Hey everybody, we are starting Unit 2. Make sure that you put your name on that front cover and let's get started. So we're going to be starting to talk about polynomial equations, and polynomial means many, right? Many, where we have different degrees of expression. So the definition of a polynomial is that a polynomial function of variable x with a degree n, where n is whatever the highest degree is, looks like this, where we have our highest degree n here, put it in blue, and it's in descending order. So the next exponent is one less than it. The next exponent will be one less than that until we get down to the constant term with no variable. Okay, remember this is a review, but the average rate of change is a fancy way of saying slope, where we take the change of y over the change of x, which is also the rise of the run. We can also call this the velocity when we're talking about something that is moving position. So let's talk about different forms of specifically linear equations. One is the general form, and we say that this is let me put this in this, ax plus by equals, plus c equals 0. So just like standard form of a quadratic, we have it set equal to 0. We've got values for a, b, and c, as long and a also has to be greater than 0 when it's in standard or general form. Slope-intercept form, you've seen this before, is y equals, and we'll use mx plus b. And then point slope form, we know it's y minus y1 equals m times x minus x1. Okay. So if I'm identifying a polynomial function, so for example, if we find the degree and the leading coefficient, if possible, for the functions below. So remember that the degree is the highest exponent. So for example, a, this right here is 4, which tells me it's the highest exponent because if I look here, there's this invisible exponent of 1. So I know this is the degree. So that tells me that the degree is 4. And the leading coefficient, so because this is the term with the degree in it, this is now what we call my leading term. If this was in descending order, it'd be at the beginning. So this value here is my leading coefficient, which is the number that's multiplied in front of the variable. So is this a polynomial? And we say yes. This is a polynomial because all of the terms in it qualify as a monomial. We don't have any variables in the denominator, and we have only positive exponents. So let's look at part B. First things first, when I'm looking at this, I notice that there's a square root, which means, remember, if I have x, or the square root of x, this is equivalent to x to the 1/2 power, which is a fractional degree. Okay, so if I've got x to the 1/2, that's like saying 25x to the 4th plus 9x squared all to the 1/2 power. So because we have that 1/2 here, we say that there isn't a specific degree because this technically is not a polynomial, and therefore there is also no leading coefficient because a polynomial will have a whole or greater than a value that's whole and big and positive. Okay. Part C, it says, hey, let's look at these degrees. So one of the things I notice here is that this is a negative exponent. And so we say we know that polynomials cannot have negative exponents because that would be equivalent to 8x to the -3 would be like saying 8 times 1 over x to the 3rd, we can't have variables in the denominator for it to be a polynomial. So we say it's not a polynomial, so therefore we do not have a degree, and neither do we have a leading coefficient because it does not qualify as a polynomial. Let's look at this one. We've got exponents 2, 3, 1, and this is a whole number, -1/3. So if I were to look at our leading coefficient with our biggest degree, this 3 is your biggest degree, so we know the degree is 3. And the leading coefficient right here is -5. We also know this is a polynomial because every term in this expression is also considered to be a monomial. So we say, yes, this is a polynomial. So this one, for example, number 2, we've got, write an equation in slope-intercept form. Remember, slope-intercept form is y equals mx plus b for the linear function such that f of -4 is 9 and f of 0 is 3. So remember, this just means, hey, when x is -4, the value of y is 9. And this means when x is 0, the value of y is 3. So we happen to know anytime that your x value is 0, this is a y-intercept, aka your b value. And then this is just a point in the line. So what do we have? We've got y equals m, which I don't know yet, x plus b, we just found out was 3. So in order to solve for m, we could do two things. We could literally find the slope based on these two points and put it into slope-intercept. Let's just go ahead and do that. So in order to find the slope, we're going to take y2 minus y1 all over x2 minus x1. So again, that's the change of y over the change of x, and we get 6 over -4, which reduces to -3 over 2 as your m. So that's going to go right here. So we've got y equals m x plus b. And that's your slope-intercept form. Example number 3, write an equation in point-slope form. So remember, point-slope is y minus y1 equals m times x minus x1. So anything in black is going to stay there. The things that we're changing are the values of the slope, or m, and x1 and y1. So what do we know? What are we given? So we know we're given when x is 5, the output or the y value is 7. So we've got this point here on our graph. We also know that when x is 3, the output is -3. So 3, -3. So we can use this to find the slope. So we're going to find the slope using the difference of the y's, or the change in y. So here's my y2 minus y1 all over x2 minus x1. Simplify, we get 5. So my slope is going to be 5. Now, in order to find the point, I can literally use either of these points. It does not matter which one you choose. I'll let this be my x1 and y1 because it was my first point. So we're going to rewrite this as y minus y1 is 7 equals m times x minus, and then our x1 is this value right here, 5. And that's our point-slope form. Hopefully that's a good review for you. Okay, let's talk about quadratic functions and their graphs. So a quadratic, remember that it's anything with an x squared largest term, which means it has to have a degree of specifically 2. We call this shape of the graph a parabola. Okay, so if this is a standard quadratic form, we know this is y equals a x squared plus bx plus c. And we know a has to be not equal to 0. Otherwise, it would not be a quadratic term. If we have the vertex form of a quadratic, that means that we have the vertex readily available in this form. So we're going to say y equals a parentheses x minus h squared plus k. And this is when your vertex is the point h, comma, k. Oh, I should have put that here. That's okay. And then our axis of symmetry is always x equals whatever our h value is. Okay, I'm also going back to the vertex. If I don't know the vertex, if it's in standard form, I can say that the x value of my vertex or my h value is negative b over 2a. And that to find y, I would plug that value back into the original function. So you'd evaluate the function at that value of negative b over 2a to find the y value. The axis of symmetry can also be found using that same value of the x value of the vertex, negative b over 2a. If it opens upward, if the parabola opens upward, we know that the a value is positive and greater than 0. If it opens downward, then the a value is less than 0, aka negative. So this one's positive, it's upwards, negative if it's opening downwards. The y-intercept tells me that when I plug in a value of x equals 0, it's going to give me c for my standard form. Therefore, that y-intercept is 0, comma c. If it's in standard form, it actually gives you the y-intercept readily available. To find the x-intercepts, you're going to solve the quadratic. So you're going to set it equal. So set f of x equal to 0 and solve. And the way that we can solve it is you can always use the quadratic formula. So sing it with me. X equals negative b plus or minus square root b squared minus 4ac all over 2a. You could also use other strategies that might work, like factoring or completing the square, but using the quadratic formula will work every single time. All right, let's talk about perfect square trinomials. So this is a specific pattern where the middle term is twice the product of the binomial's first and last term. So what does that mean? Here's what this means. So if let's say you've got x plus some value, we've seen this a million times, that tells me that when I FOIL this out and combine my like terms, I'm going to end up with x times x is x squared, x times a, which is a times x, but then I'll end up with another x times a, so that will give me 2 of them. And then, of course, we know the last term will be a times itself. So this is the pattern that we'll see every time when we're foiling something that looks like this, where we have the same factor squared, meaning the same factor times itself. If I have x minus a quantity squared, this pattern will be x squared minus 2ax plus a squared. Same idea that we're squaring the first and the last terms, and then when we FOIL those x times negative a, we double it as well. So how do we complete the square? So hopefully you remember how to complete the square. This is a review, but here's our steps. Here's the procedure to convert from standard form, so from standard form to vertex form using completing the square. So first, if the a value is 1, you can, I like to say, make some space. And you're going to rewrite this so that it's like y equals x squared plus bx plus, and you're going to make a space here, okay? Put your c value out here, okay? In order to find what's going to go here in that space, we're going to find, now we're going to complete the square. You're going to take your b value divided by divided by 2, so half of b, and you're going to take that whole value squared, okay? And this is the value, the exact number that you need to complete the square, or to make it a perfect squared factor. So this is what's going to go in that box. You're going to add this value to create the perfect square trinomial. Next step, we're going to actually balance the equation. So because I can't add some random number to an equation without balancing it. So I'm also going to subtract the same value from that value of C to get your new K value. And this again is for your vertex form. And then our last step is that you're going to factor and simplify to get y equals a times x minus h squared plus k. Okay, so let's use that step, those steps to go ahead and complete the square to find the vertex form. So here's my standard form. If I were to write this out, I know I would get a, b, and c are 2, -8, and 11. So in order to do this, I'm going to go ahead, I'm looking here. If a equals 1, we would isolate it. So, but here's the deal. Is a 1 here? No, it's not. Okay, so what we can do to find the vertex form is find what the vertex is, okay? So in order to find the vertex, remember from vertex form, I know that x equals -b over 2 times a. So I know negative times b, which is -8 all over 2 times a. That's going to be +8, negative times negative over 4 is 2, is my x value. So if x is 2, this is also the equation of your axis of symmetry. Okay, but we also know that our vertex will be 2, and then we have to find our y value. That tells me that we're going to plug into f of x, f of when x is 2. So let's evaluate it. 2 times 2 squared minus 8 times 2 plus 11. And we're going to look at this. 2 times itself is 4, times 2 is 8, minus 8 times 2 is 16 plus 11. And we get -8 plus 11 is +3. So if f of 2 is 3, then the vertex is when x is 2, y is also 3. So we've got our vertex here as well as our equation for the axis of symmetry. Therefore, our vertex form is y equals a times x minus h quantity squared plus k. And then we're done. All right, let's use completing the square to describe the graph of f of x equals 2x squared plus 4x minus 1. So now we're actually going to complete the square, okay? So in our first step, if a isn't 1, we have to make it equal to 1. So what we're going to do is first I'm going to rewrite this. So I've got f of x equals 2x squared plus 4x minus 1. So what we can do with this is I want this a to be a 1. So I'm going to take these two pieces and I'm going to factor out a 2. And I get x squared plus 2x. Okay, here's this minus 1. I'm going to put it right here. In order to know how to complete the square, I'm going to create this space. What goes in here? Remember, we're going to take b, cut it in half, and square it. So here's your b value is 2. Cut it in half and square it. So I know 2 over 2 is 1. 1 squared is just 1. That's what we're going to put in this box. This will complete the square for us. Once we put it there, our next step is to balance what we just did. We can't randomly just add 1. But that 1 isn't just being multiplied. It's not just a 1. It's actually also being distributed by a times 2. So the value of this 1 here is actually 1 times 2. So I'm going to subtract a minus 2 here in order to balance out that equation. Now we're going to factor. So we've got 2 times, and then this becomes a perfect square trinomial. So this is going to become x plus 1 quantity squared, and this simplifies to minus 3. So we're left with 2 times x plus 1 quantity squared minus 3. This looks like it's in vertex form, and we can, from here, find our vertex, and we can also solve, okay? It says, use completing the score to describe the graph, support your answer. So we know that the vertex will be at -1, -3, because this is our x minus h squared minus k all times a. So here's our vertex. We have an axis of symmetry where x equals -1. We can also find the zeros or the roots, aka x-intercepts, if I set this equal to 0, because remember, x-intercepts are when y equals 0. So if I say y equals all this, we can say 0 equals 2 times x plus 1 squared minus 3. Let's solve it. Add 3 to both sides. I get 3 equals 2 times x plus 1 squared. Divide both sides by 2. We get 3 over 2 equals x plus 1 squared. Take the square root of both sides, plus or minus. I get x plus 1 equals plus or minus the square root of 3 over 2, minus 1 on both sides, and I get -1 plus or minus the square root of 3 over 2. Keep in mind you want to rationalize this because you can't have a root in the denominator, so this is technically equivalent to -1 plus or minus root 3 over root of 2. I'm going to rationalize it by multiplying both top and bottom by a root of 2. So this is really x equals -1 plus or minus root of 6 over 2. And those are our roots. So how do we do this? Our vertex we know is -1, -3. Our y-intercepts back from our original standard form, our c value is your y-intercept. And our x-intercepts are these values of x. So we know that it's the point when x is -1 plus the root of 6 over 2 comma 0, and the value of x -1 minus the root of 6 over 2 comma 0. Okay, so now let's model some free fall motion. So if you're in physics right now, you might have seen this, okay? So think about when we're talking about a height of some sort of object that's falling, where the forces of gravity affect it. So this is our formula that the height or position is s of t equals -1/2 times the force of gravity times time squared times, usually in seconds, plus the initial velocity times t plus the starting position. And our vertical velocity equals negative times the force of gravity times the time plus the initial velocity. Okay, and keep in mind where t is in time, in seconds, the force of gravity is 32 feet per second squared, which is approximately 9.8 meters per second, and that's the acceleration due to gravity. We say v naught, or v sub o, is the initial vertical velocity of the object, and s sub o, or s, this tells you what happens when there's no time, hasn't passed yet, is the initial height. That's it for now. We're going to do all of the applications of this in class together.